So let us begin this particular webinar. So this is the first webinar among the series of webinars that will be offered by LearnCX. You must have gone through our website and you must already be knowing a lot of things about this particular training portal, and you will get to know more details about it in this particular webinar. So this webinar is titled Role of CFD in Engineering Design. It is brought to you by LearnCX, which is a training organization which provides online training in the field of CFD and CAD. So let us have a view of the roadmap that we are going to follow in this particular webinar. First, we will have the welcome and introduction. Then we will go through the webinar presentation in detail. We will take your questions after that. And then we will close this particular webinar with the closing comments. So firstly, thank you for your registration. Before we begin this particular webinar, thank you for your registration and attending this particular session. Please note that this is an introductory webinar. This is the first among series of webinars that will be conducted by LearnCX. What I mean by an introductory webinar is that this particular webinar is designed for individuals who are either new to CFD or have very little knowledge of CFD and are curious about this particular field. So if you already know a lot of things about CFD, or if you are familiar with this field, then you might be knowing a lot of things in this webinar, but still it is worth going through. So now about LearnCX. LearnCX is the training division of CC Tech, that is Center for Computational Technologies, which is a engineering services organization based in Pune, India. We provide industry-focused courses for CAD as well as CFD. And our model is to provide training in the field of CAD and CFD by using online training methods. And our model is as close as possible to the interactive training methods which are conducted in class. We provide interactive ways in which we can interact, in which the student can interact with the faculty, and the lectures can be viewed online at their own comfort. Just an overview of this particular webinar. First we will see what is CFD. Then we will go through entire CFD process flow. We will see what happens behind the CFD solver or in the background of the CFD process. We will see how CFD is used in design cycles. We will get to know some of the commercial CFD packages if you don't know them already. Then we will see some applications of CFD, some fields in which CFD is commonly used. We will also go through a detailed case study using CFD, a design problem that is solved using CFD as a sample problem. And in the end, we will see what does LearnCX, or what do we offer for individuals who want to get trained in the field of CFD or CAD. In the end, I will take your questions and we will end this webinar. So first we will have an introduction to CFD. Now, whenever we see any phenomenon related to fluids that is happening in nature or in industry, we observe that it is visually very pleasing to the human eye. Let's take an example of this particular image. All that is happening behind is fluid mechanics or physics, even in this case. But it appears to be very pleasing to the eye, so generally it is always said that fluid mechanics is equally an art as well as science. It is very pleasing to the eye, but there is a very complex physics that goes on behind it. So to understand this fluid mechanics, various techniques are used. This is used since a long time, and various techniques have evolved now. Basically, it is established that fluid mechanics is studied in three ways. First is experimental methods, conducting various experiments. We can also use analytical methods or theories or empirical formulas that are been developed since a long time. And lastly, the computational methods called as CFD, in which computers are used in order to understand fluid mechanics or fluid dynamics. So what is CFD? CFD is basically a science of predicting fluid flow, heat transfer, or any transport phenomenon like mass transfer, chemical reactions that are associated with fluid flow. These phenomena are studied by using mathematical equations which are solved using computers. So within CFD, what we get is a qualitative and quantitative prediction of fluid flow by using mathematical models, numerical methods, and all these mathematical models or numerical methods are clubbed into a software tool which solves these equations. So when we do CFD, it is basically a three-step process or three-stage process. First is doing pre-processing, in which we create geometry, we clean up the geometry that is involved, we do mesh generation, we apply boundary conditions. So the first step while doing CFD analysis is pre-processing. An example of that is shown here, where a impeller blade geometry is converted into a CAD geometry which will be used for doing CFD. Similarly, an example of a truck geometry which is converted into a problem or a CAD problem, and this particular CAD model will be used for analyzing from CFD point of view. The mesh generation, that is dividing the entire CAD model into different small cells, is called as meshing. As you can see here, this particular geometry is divided into small grids or mesh. This is also part of the pre-processing. Another example is a compressor geometry which is again divided into grids or mesh. Next step or next stage is solver stage, in which we define our problem from physics point of view. We attach additional models for solving those physics. We use various numerical computational techniques. So the second stage is solver stage. As you can see, a particular solver is used. It can be a commercial solver or an in-house code or any other mathematical program. To that, we input material properties, boundary conditions to define the physics involved. We input the equations that are needed to be solved. We input the solution algorithms, various mathematical control techniques, and we input the grid, the CAD model along with the grid. So all these are used by the solver, and it gives us the result of the mathematical equations within that domain. The results that we get, we have to analyze those results in order to make sense of those. So that process is called post-processing, in which we visualize the results in the form of contours, colored contours, vectors, path lines. We also can view data in the form of drag, lift, and other average values. So the last step is basically utilizing the data that is generated by the software and post-processing it in order to make sense and in order to extract design decisions from that. An example of a post-processing is shown here, where pressure contours are plotted along the centrifugal compressor and along a plane within that centrifugal compressor. So now let us see what happens behind this process, in the sense that what is solved and what goes on in the background. Now whenever we do simulations, we have to basically solve for physics or understand physics in detail. The physics that we are solving can be a fluid flow or heat transfer or phase change, solid mechanics, and various other scientific phenomena. So in order to visualize or understand this physics, we can use either experimental analysis or mathematical equations which describe that physics. So experimental analysis is a whole different field, so we will not go into detail in that. But within the mathematical equations, we can solve these mathematical governing equations by using analytical theory or by using numerical solutions. Numerical solutions is an approximate method by which we actually convert these mathematical equations into algorithms and then apply algorithms to solve the entire physics involved. So when we say CFD, what we mean is we solve the physics using mathematical equations which are converted into algorithms by using numerical techniques, and various different algorithms or models are used in order to simulate that particular physics. So this is the path which CFD follows. That is, physics is converted into mathematical equations which are converted into numerical equations, and those are solved by using different algorithms. The softwares that are commercially available use either the finite difference method or finite element method or the finite volume method. So this is the path followed by any CFD software or any CFD code. So now let us see the process of CFD in detail. First things first, we have to convert a physical problem into a mathematical problem or a CFD problem. For that, we have to assign different governing equations to it. We make different simplifying assumptions, that is whether we are going to solve a steady state problem or incompressible problem. This is all done by understanding the problem and whatever physics is happening, and then utilizing that understanding to define a CFD problem. We come up with a CAD model for that particular physical phenomenon, and then we assign different conditions or physical conditions or boundary conditions to the CAD model. As shown here, this particular heat exchanger problem is converted into a CAD model, and different type of boundary conditions or physics is associated with that by using our problem understanding. Next is we have to mesh. We have to mesh this particular CAD model in order to convert that CAD model into large number of small cells or grids, and within these grids the mathematical equations will be solved. So what the CFD do is it applies the numerical methods or mathematical equations to these small cells. As you can see, the same model of heat exchanger plates is now divided into small number of cell volumes or grids. This process is called meshing. So we divide the entire domain into small number of cells or volumes called grids or mesh, and the equations are solved in each of these meshes. This is applicable for finite volume method. Next is we put all these CAD model along with the grid into the solver, and the solver solves algebraic equations or numerical equations on a computer using commercial code or in-house programs. So the mathematical equations which are converted into numerical equations are solved at each particular cell or controlled volume, and such process is repeated through each grid in order to solve the mathematical equations for the entire domain or entire CAD model. Once we do that, what we get is basically a huge number of data or numbers. That data or numbers has to be fit into useful form by using various representations like contours, vectors, path lines, etc. As you can see, some of the contour examples are shown here. Now what will we do with all this data? Basically, a CFD engineer has to analyze this data and make design decisions based on that. The fundamental knowledge of fluid mechanics and heat transfer and any other physics like combustion comes into picture when we analyze the data, and we have to. So basically what CFD solver will give you is just this data in various forms that you want, and you have to make sense of it. So where do we use CFD whenever we go and design a particular product? Nowadays, considering the current market scenario or a current innovation cycle, there is a huge competition for every product. Customers are becoming more demanding, and there is very little time for marketing or developing a new product. So what does that mean is for a particular product, for innovating or developing a particular product, there is very little time, so the entire product development cycle is very short. The effect that this has is that to make a new product, we have to be highly efficient, and the cost of product development has to be reduced as well as the time. To do this, the only way is to make better design decisions when we develop any new product. And simulations play a huge part in making better design decisions. So simulations have become an integral part of any product development cycle. As far as using simulations, it is observed that the more innovative or more successful product development companies, or research organization, what they do is they use simulations or CFD in the design phase itself, rather than using it at a later stage when they have problems in the product. They use or integrate the entire simulation process within the design phase and come up with the best possible product, test the performance of those products by using simulations so that whenever they launch a new product, it will be the best or ideal product from design point of view. So what they do is they basically convert a design problem into a CFD problem or a simulation problem. They do something called as experimental design, where they come up with various design variables, and in order to see the effect of that design modifications or variables, they do simulations where they see effects of those design changes in the simulation. So the CFD simulations that they do gives a large amount of data which has to be managed, and design modifications have to be done using that CFD simulation. So data analysis and design decisions become a critical part, and the effect of those design changes or modifications is seen using CFD simulations. Now, why has CFD become so popular or so mainstream in the design cycle? Basically, there are three reasons. One of them is the computational technology has advanced to a great deal. We nowadays have huge memory computers or huge RAM computers which are highly cheap. So we can couple those computers together to solve large amount or very complex physics as well as very complex mesh size. There also has been continuous effort by the CFD software providers to implement various complex physics models. And also new numerical algorithms or techniques are continuously developed and published, which can be incorporated in order to solve a complex CFD problem. So all these three reasons have contributed into CFD being a mainstream design tool. If you can see, this is just a data where the number of published papers based on CFD have gone on increasing throughout the decades. So if you see in the decade of 2000, we see large jump in the papers that are published which reference. Now let us have a look at the commercial CFD softwares that are available. You may be knowing many of them already. The popular ones are ANSYS. ANSYS as a company provides a huge range of simulation tools. One of them is Fluent, which is a CFD package. Another one is CFX, which is also a CFD package. And ICM CFD, which is used for meshing. There are other packages or other softwares also provided by ANSYS, but we will not focus on them in this particular webinar because this is focused on CFD mainly. StarCD, which is provided by CDI is also a very useful or very popular tool, which is used for solving for modeling CFD problems using unstructured mesh. Simulates any physical problem using partial differential equations. There are other packages like OpenFOAM and Flow3D. There are a lot of other CFD packages or CFD softwares which are available in commercially, and you can use them depending upon what your requirements are. So now we will see some of the applications of CFD in various popular fields or various industrial fields. Within the automobile field, CFD is used for modeling air handling systems or engine cooling type of problem, exhaust and intake manifolds, for modeling external aerodynamics. In motorsports, it is widely used, and also in modeling combustions, as well as indoor and outdoor passenger comfort. Another popular example is electronic cooling, in which CFD is used for modeling the component level and the assembly level cooling problems. They are also used in equipment modeling. It is also used in storage devices, modeling the cooling requirements of storage devices. In HVAC field, it is widely used in seeing the airflow around buildings. Some of the designs like burner design, fan noise, environmental control systems, heating requirements and cooling requirements of indoor environments, as well as duct and walls and fittings modeling, the flow through those. It is also used in indoor room flow distribution modeling. In the aerospace field, CFD is also well established. It is used for combustion modeling, external aerodynamics, for fire separation type of models or simulations. It is used for inlets and nozzles and other parts or other component flow modeling. It is used in propulsion modeling also, as well as pumps and what CFD is and how it is used in design cycles, as well as what happens behind CFD. Now we will see a small sample case study which shows how CFD is used in order to modify design or optimize a particular design. So this sample case is of a boiler outlet duct system design using CFD. This is a CAD model of that particular duct system. There is flow through these ducts, and it is important to analyze this flow because it offers resistance to, in order to model these, because it offers resistance to the flow. That is, the duct system offers resistance to the flow, and this resistance causes a pressure drop, which is provided by the power, this pressure drop is actually compensates the power. So we have to optimize the entire design in order that the pressure drop is less and less power is required in order to drive the flow through this duct system. So objective of the problem is to minimize the pressure drop and to come up with a design with a design which actually gives least pressure drop. So what is the physics involved is we have to study various physics involved in this particular problem, that whether the problem is incompressible or whether it is steady or unsteady, whether we are using a single phase solver or a laminar or turbulent flow. We have to decide the CFD domain and boundary conditions for our CFD problem. We also have to decide what geometry are we going to use, which type of domain do we need, whether we can simplify the geometry, and also what type of mesh are we going to use. Now all these parameters that I just mentioned are terminologies that are associated with CFD, and if you are new to the field of CFD, you may not understand this right now, but once you are very well familiar with this field, these are day-to-day terminologies that are used by a CFD engineer. So our problem is basically to optimize the design or in order to ensure that minimum pressure drop occurs for this particular duct flow. This is the flow inlet and this is the flow outlet for this particular problem. The flow comes from here, goes to its ducting system, and its outlet is from here. The CFD solver that we are going to use is an incompressible steady state flow pressure based solver. We are using the realizable K-epsilon turbulence model. We are going to ensure that continuity is balanced throughout the domain when we solve it. The convergence criteria of 1E minus 3 is used, and also second order upwind scheme is used. Again, these are all related to CFD, all these terminologies and solver terms. So don't worry even if you don't understand them right now. Before we go into solver, we have to mesh the domain, and as seen here, we are using a structured multi-block technique in ANSYS ICM CFD in order to mesh this particular ducting system. Now let us see what are the results for first existing design. These are the pressure contours, velocity contours, and path lines for this particular design, and we see that the change in the pressure is happening within this connecting channel. That is the pressure drop that we are going to see. So in order to reduce this pressure drop, we go on changing the design iteration by iteration. That is, we do CFD for this existing design, then we change this design as seen here. We are modifying this connecting section and do CFD on this also. We observe the pressure drop. If it is not satisfactory, we change the design again, and then we change the design again, and we come up with the final design, which is called iteration 4, design iteration 4. We have observed that for this particular design iteration 4, the pressure drop that we are getting to drive the flow through this ducting system is minimum. These are the results for the final design, and we observe that the pressure drop is reduced. It was observed for this particular design change that the pressure drop for the final design is reduced by 80%, and all these observations or visualization has been done using CFD without actually developing a prototype. So such design iterations or design changes and modifications or design optimization that we call can be done using CFD simulations. Now, the question that may come up in your mind is how to get involved or introduced to this field of CFD if you don't know much of it. So, apart from fundamentals of fluid dynamics and heat transfer and mechanical engineering, some sort of introduction to CFD is needed, either in the form of training or learning it from your own. So, an individual or a CFD engineer must be well familiar with fundamentals of fluid dynamics and thermal sciences. They should have an introduction to fundamentals of CFD, and they should also be trained in how to use CFD software. It is also important to know how CFD is used in design. And after doing CFD, it is extremely important to know how to make use of the CFD results, how to make design decisions based on CFD results. So all this forms part of a CFD-based training. So we here at LearnCX offer all such type of training into our model courses that are offered online. What we say is, instead of being confined to rigid classroom trainings in which the course as well as the timelines are very rigid and they do not suit to individual needs, instead of being confined to this classroom training, why not be part of a revolutionary or a new form of training methodology that LearnCX offers? Now, what LearnCX offers you is an online training which is conducted through the internet-based training management software, which imparts model design courses which are related to the field of CFD and CAD. What we offer is different type of courses which are delivered at your doorstep, and you can just go through these courses at your own comfort using just an internet connection and a computer. You don't need to travel. All the resources are available at your desk. It's cost effective. You can go through the material any number of times. It is just available during the course duration. There is no fixed timing of lectures. All the lectures are available for you to view at any number of time, and you can go through them and ask your questions to our faculty using interactive sessions also, which are conducted live. There is a huge library of lectures and tutorials prepared by our faculty, and all this is available through a learning system which is delivered to a computer. So instead of getting stuck in old times, you can get a highest quality of CFD and CAD training in a cost-effective, efficient, and cool way, that is through online, which is offered by LearnCX. Currently, we have 4 courses that are available through our portal. First is CFD modeling using ANSYS ICM CFD and ANSYS Fluent. This is an introductory course to CFD in which we cover the basics or fundamentals of fluid mechanics, CFD, heat transfer, and then we deliver introductory training using the softwares ANSYS ICM CFD and ANSYS Fluent. Another course that is available is an advanced course on multi-phase flow modeling using ANSYS Fluent. Next course is also an advanced course which is on heat transfer modeling using ANSYS ICM Fluent. The 4th course that we are currently offering is a computer-aided geometric design course. This is a programming course which introduces the user to the advanced topics of computer-aided geometric design. It involves coding as well as programming. Now, how can you reach us for all these different training courses? You can sign up on our website, which is learncx.com. This is a free sign up, and there are various free demos and free lectures that are available that you can go through. There is huge knowledge base, and that does not require any fee. You can just sign up and go through these lectures. If you want to register to our courses or take admission, there is a separate process. But this course is available. Some courses and demos are available free that you can access by just signing up for free. You can also visit our blog, that is blog.learncx.com. You can reach us at Facebook. You can find us on Twitter also, as well as YouTube. But the best way to contact us for your individual needs is by emailing us at info@learncx.com. You can ask any questions that you want, and our course coordinator will get back to you either through phone or email. So this is the email address to remember, that is info@learncf.com. We offer individual training as well as corporate-based trainings or corporate programs and customized programs as well. All this is just offered to your doorstep. You don't need to travel. You don't need to be very rigid with your schedule. You can view the courses around your professional or academic schedule. So by this, we just end our webinar here, and if you have questions, we can take those questions now. So I hope this webinar was useful for you, and thank you for registering and attending this particular webinar. Again, if you have any questions, you can just email us at info@learncf.com. And I hope in the future you visit our training portal as well as you interact with us for various training needs of yours. So thank you for attending this webinar, and we are ready to take any of your questions now. Thank you.